but it's concerning a binomial distribution. You just want to fit a binomial to this, okay? And you don't know P, you have to estimate it. P hat is it's a total number of successes over the total number of trials. So
Can you focus that? Can you focus that a little more?
sorry?
It's hard to read a little bit.
It's number 9.
Anyway, P has a total number of successes. So in this you had you had 7 no successes, right? And then 36 1 successes. And downstairs you have you just add up 10 times, actually 10 times it.
And
Is it 500? So this would be 500. Then once you have P hat, you're set. You have to get a binomial distribution. And tables really aren't going to help you there because it's going to come out to a decimal, right? It's not going to be in that table for the most part. Unless it's a textbook exercise. So you could either get that. Why don't we just do it with Minitab? I'll show you how to do it with Minitab. But once you get this, the expected frequency, the probability of binomial A. P hat is equal to I, right? But that would be the expected frequency. And then in R, this would be D binomial. Okay. You could get them all at once, sir.
And by hand, it's just 2 pieces.
It's, yeah, you don't want to.
Yeah.
Don't do it by hand. But you can get them all this way. Now, how do you do it? Then in Minitab, what you want to do is you do the same thing. That's what I would do. And then you can use the hopefully. I think it's PDF. Okay. We'll put these in C1, and do PDF C1 and C2, and then find it. Okay. This is still good for them. Look at PF and off to the name of who's it for? Pardon me?
I have 0.377. No.
We could take. Let's just take one lesson there. Then Minitab would be this. you use the line command. See, then in column one, you have 0 through 8, and then, I think it's PDF, we'll see, PDF, C1 and C2, and then, final, 8, and 4. So, remember it would be a bit skewed right, to do histogram. Oh, that's crazy, isn't it? Just forget that. Well, yeah, it's one, so we do this. It should peak around 10. It does, it's 0.277. Then you could, here's your expected frequency, right? So there's your expected frequencies. It's close, right? 736, 105. And with many tab, what you could do is you could set the frequencies into another column. And then the test would be what? It's just take the sum of C3, right, minus C4 square, and square mini tab is Fortran, right? Hello star. It still exists. What's that? Divide by C3, the expected. Okay, you have, you actually have 9 categories, right? 0 through 8. So you have 3 categories, and then you had to make an estimate, so you're down to 7 degrees of freedom. Okay? So your little low, you expect around 7 for your test statistic, comes out around 10. So what you could just do CDF, K1, and then K2, and this would be chi, right? It's heights, and then we add what? Yes, 7 degrees of freedom. So you're not gonna reject it's 0.186. Okay, any questions on that? Yes?
Will it be 6 or 7 degrees of freedom?
6, you have 9 categories, right?
Oh, you have 9, yeah. I agree.
Any other questions? Okay. Okay, well then, today let's continue talking about the sine and cosine and then we'll have a quiz. Last time we started talking about the sine and cosine. I believe that's it. Yeah, passage. We switch terminals on the computer. You can't see it, so it's many micro, small micro seconds. So we talked about the sine rank Wilcox last time. Now we're sampling from something like this, sort of symmetric, and again, the sign test just asks which side is the observation on, to the right of theta, to the left of theta, minus, plus. And then the t-test goes too far because it actually uses the observation. And so something in between is just to rank the absolute distances, right? And that's the sine rank Wilcox. I'm going to do an example on the sine rank. Let's just go through the other pieces of it. And then we'll finish with the example. We have these x's, right, and then we're still testing the same hypotheses. And it is the median, that parameter does not change. Although with symmetry, it can be the mean too. Plus. So that's our process or our statistic. It's our test statistic if this is theta non. We took the expected value under theta, 2 plus theta is n times n plus 1. Now there's a basic identity here, and it's not obvious at all. And the identity is this d plus of theta is also equal to the number of Walsh averages, which are very theta. Now these pairwise averages are called Walsh averages. And you only get a half of it. Okay, but if you do then, you can calculate this sign rank Wilcox in that way. Okay. Now, for an example, here's a big example. Here's my big data set, right? And we could calculate the sign rank Wilcox and when you stay equal to 0, so 1, 2 plus 0 would be the sum of the ranks you want for the size greater than 0, you want the sum of the ranks of the absolute deviations, right? But if theta is 0, so that would just be 0. So this would get, when you take the absolute value, this gets rank 1, this gets rank 2, 3, 4. So this, of course, comes out to 9. Right? Then what are these Walsh averages? They're pairwise averages, and you can, if you do it by hand in the old days, that's the biggest example you have to do. You want those pairwise averages, so you just put the data down in order. Makes it easy, as you can see. Cross the tops and cross the bottom, and then you just calculate the averages. And you just have to get this.
How do you rank the same x size?
Right? You take the average of ranks. So here we don't have any time. If this is -4, then this would have rank 1.5. This would have rank 2. And then you start with 3. Okay, 1 and 2 are gone. -2 plus 4 is 2. Divided by 2 is 1. This would be 6. This would be 10. And then you just get the, you just need the upper part of the table. So there are my Walsh averages. There's always n times n plus 1 over 2 Walsh averages. So in this case, n is 4. So there's 10. There's 10 in this table. 4, 7, 9, 10. And how many are greater than 0? 9. So checks. Now that gives me the estimate. The other way doesn't. See if you can figure out the estimate from the other way. The estimate is just like we did with the sign test. Okay? We want you never reject this one. Okay? If you can choose your hypotheses after you get the data, and you don't want to reject H0, you know exactly how to choose your hypothesis. And so I want to solve this. It has to come out to the expectation. Try to solve this. How would you solve that? Well, of course, what you use is the advantage. There's the advantage. rewrite this for a moment like this, and you can tell me the answer. There are n times n plus 1 over 2 Walsh averages. And how can you pick theta hat so half the Walsh averages are greater than theta hat? It's what? What's theta hat? What's the magic number? The value. There are n times n plus 1 over 2 Walsh averages. And I want to pick theta hat, so half the Walsh averages exceed theta hat. It's half, it's 1/2 n times n plus 1 over 2. The answer is what? 0. It's not the mean, it's the median. Just take the median of the Walsh averages, and half the Walsh averages will exceed it, and half will be under. It works. It's just the median of Walsh averages. And this is sometimes called the Hodges-Lehmann estimate. Named after 2 statisticians, Hodges and Lehmann. They're both dead now. Lehmann just died a couple years ago. They did some fundamental work in physics. Okay? You would never guess that from this one. It would take you a long time. So then back to our huge example here, mean of the Walsh averages would be what? There are 10 Walsh averages in this table, you just have to come across the ordered 5th and 6th. So if you have a small sample, this little table really helps, right? It's like in a partial order, and the idea is to drift this way through the table. And this is the lowest Walsh average. So this is 1, 2, 3, well, this is easy. 4, 5. And this would be the 6, so the answer is spot number 5. So the theta hat. See, the median would be the average of these two, which is 6, right? Well, we should use theta hat for that. Let's just put the HL on the bottom. So the median is, let's say, 6. The mean is 24, 22 divided by 4. The mean is 22. So it would be 25. It's the same as the Hodges-Lehmann tends to be robust. It's not as robust as the median. The median, you have to shift 50% of the data to infinity to affect it. How about the Hodges-Lehmann? It's 29%. It's more robust than the quartile. Again, 50%. Roughly median. 0%, well, I'd say, minus. Now notice that if it's a big problem, in fact, I had an example. I don't know where I got this data. Yeah, here's some data. So there's 1, 2, 3, 4, 5, 6, 7. So there'll be 7 times 8 divided by 2. There's 28 Walsh averages. It just gets to be a mess, right? 7 is a very small data set. There's my table. There's 28 Walsh averages in this data set. Well, we would spend it. In fact, there's there used to be rules you could do for approximations. I don't remember it at all. So you don't want those. Okay. Now there used to be a command in Mintab to get the Walsh averages. We can try that in a second. We get a confidence interval the same way. I mean, it just works out the same way. You just look at you order the Walsh averages and you pick off certain values, and that's your confidence interval. And then from that you get an estimate of standard error. So everything goes through immediately. So when you have the axes, right? Then you compute the Walsh averages. And then you just order it. C is actually it's the menu. See, after a while you even remember it. And then you have the variance. So minus alpha times 100%. CI, well this would be 95%. I should put the Z critical. It's just C plus 1. Then the minus. And then you can do the standard error the same way. There's I'll call it tau half. We'll talk about the parameter in a moment. You might put a sub W on here. You might do Wilcox. The estimate is root n times 90 is confidence interval divided by 2 times z. Usually we use 95%. And then this here at theta n. On Zeeman is tau hat W. Okay. Now, these, of course, aren't any easier to get than the estimate. You still have to do the table of Walsh averages. And this gets to be a big problem, okay? You know, a moderate sample size is around 20 to 30, say 30. Then you have what? You have over 450 Walsh averages. It's not going to do that by hand, okay? It has to be computed. But this is the age of the computer, all right? 30 years ago, we probably wouldn't be having this conversation. Although the estimate is. I'll just try to all see through. Yeah, it still works. So with Minitab, we can get the Walsh averages and then we can order. Okay? So let's go back to this data set I had. Oops, now you can see it. And we just get the Walsh averages. So let me put the data in. Let's put in C6 so we can see it. You don't have to go up in order. Okay, so now I have my big sample in, then I can just walk C6 and C7. Yeah, be careful. Minitab doesn't just overwrites. Oh, that one didn't overwrite. And then you just want to sort it, right? And then in this case, there's what, 2, 4, 6, 7 data from 28 averages. So you can just get the median. Yeah, I mean, you can let the computer do everything. Just get the median on CA. Fine. $15.75. Of course, if you print that, see. So halfway there, you get 15.5. So it should be the what? The average of the 14th and 15th. Then you could do the confidence interval the same way. You just have to get that roll. So it's going 10, so it's 7 times 8 divided by 4 minus 10. Plus 1 times 2 minutes. So you would round to 2, so you want the second word Walsh averages, and the next to the last one. See, I did that. The sample size is small. You only have 7 observations. C plus 1. No, C would be 2. You'd round it to 3. 1 to 30. So the beginning of our confidence interval would be 8. To 29. So that would be our confidence interval. Our point estimate is what, 14.5, right? 15. So that's nice, you can do it that way, I mean, and you should try to do it for a simple example. But that's not the way you want to do it. You just want to say W test or went. Default's 95%. And the data was what? C6, right? It's the data. So it's 8 to 29, just like we have, and the estimate is 15.8. They must still be using it. It's 15 and a half, but it wasn't 14. I think it was 15. I don't know what you want to test here, probably not 0. Suppose it was of interest to test W equal to 10. Oh, I forgot to check the file, but you can just do W test. You could ask for help. I forget. This is going to test 0. If I wanted, here's what I can do to test for 10. Let me just put this on top of this. And now just test for 0. Zero test for 0. Does anyone remember the value? What's the? Well, I'll find out. You could just ask for it. But there's a test now for 10 wrong, okay? Although it says 0, we subtracted 10 from all the data points. And you're not going to raise the two-sided test. P-value is 0.176, so you won't be rejected. Okay, any question on the Wilcox and R? It's Wilcox, they left out the O and on. Wilcox. And again, we have to have the data, that would be your sample, and then you can just ask for help for what the null value is. And you definitely want confidence interval equal true. I don't know why that isn't equal. It's not. Now give you the confidence interval points. At the moment, this will test 0, that would be default. Okay. You could do what we just did. But that's not good because I don't think you can honest. Let me just say null equal 10 up. We could both look for it. I mean, both look for it. I don't have R on this machine, so I can't look for it tonight. I don't want to do that because I'll have to add 10 to the estimate of confidence. It's mixing myself up. I could do them separate. You could have 2 communities. Oh, here's my confidence interval. Oh, I forgot I had to test 10. Don't pass through comments. Okay, you can do one-sided test with, I remember that one. So there would be a one-sided test. The other side would be minus 1.
Main tab sticks with that, I think, in most of your commands. Alt 1 is test and mute, null value, mute greater than null, 0 is mute not equal to null, -1 is mute less than null.
Okay. So there we discussed software for the Wilcox and then I've been saying this for the last few times, but we will begin next time with why you would choose one over the other. I mean, you have to talk about that one, right? We have 3 methods you can choose from now. I hate to tell you this, there's an uncountable number of methods. So you can eventually reject any of them. So we have to talk about why you would choose one method. And that's efficiency, and we'll talk about efficiency next time. Okay, so now we have a quiz. I don't want you to use your laptops for the quiz, I want you to spread it out.